Hello and welcome. In this session, we'll be talking about the solution to the equation of the form f of x is equals to 0 using a method that we call the Newton-Raphson iterative method. The Newton-Raphson iterative method, or simply the Newton-Raphson method. Now, the Newton-Raphson iterative method can be expressed in the form xn plus 1 is equals to xn minus f of xn divided by f prime of xn. In this equation, f prime of xn is the value of the derivative of the function f of x when x is equals to xn. So the method can be stated thus, like if xn is an approximation to the root of the equation f of x is equals to 0, then a better approximation is xn plus 1, given by this equation. So to apply this method, we start by taking an initial approximation, which we shall denote by x naught. This is an initial approximation to the root of the equation, and then we apply the method to find a better approximation to the root of the equation. Now, the initial approximation can be obtained using the techniques such as the intermediate value property. For example, we want to consider the equation. X cubed plus 2x minus 5 is equals to 0. So we want to apply the Newton-Raphson method to find the root of this equation. Now, the function f of x in this case, because we want to express this equation into the form f of x is equals to 0. So the function f of x, therefore, is given by x cubed plus 2x minus 5. So next we differentiate this function with respect to x. So we shall call the derivative f prime of x. So the derivative is given by 3x squared plus 2. So we now substitute these expressions into the Newton-Raphson formula. Remember, the formula can be expressed as xn plus 1 is equals to xn minus f of xn divided by f prime of xn. So we're going to substitute f of xn is equals to x cubed or xn cubed plus 2xn minus 5, while f prime is this expression here. So in this case, we get this is equals to xn minus xn cubed plus 2xn minus 5 divided by 3xn squared plus 2. We can probably simplify this first before applying. So we get, we can put the terms at the common denominator, 3xn squared plus 2. Then we shall have xn into 3xn squared plus 2 minus xn cubed plus 2xn minus 5. If we simplify this, we'll get 2xn cubed plus 5 in the numerator, and the denominator is 3xn squared plus 2. So this is the Newton-Raphson method for solving this particular equation. Our equation was x cubed plus 2x minus 5 is equals to 0. This is the equation we are trying to solve. So the Newton-Raphson method for solving this particular equation can be reduced to xn plus 1 is equals to 2xn cubed plus 5 divided by 3xn squared plus 2. Now we'll take the first approximation as say x naught is equals to 0.5, or rather x naught is equals to 1.5, not 0.5. Now this value, as we said, can be obtained by using the techniques such as the intermediate value property. For example, given our function f of x is equals to x cubed plus 2x minus 5, we can find that f of 0 is equals to 0 plus 0 minus 5, which is negative 5. If we compute f of 1, then we get 1 plus 2 minus 5, which is negative 2. Notice the value is negative. If we compute f of 2, then we get 2 cubed plus 2 times 2 minus 5. And this is 8 plus 4 minus 5, which is positive 7. So note that as you move from x is equals to 1 to x is equals to 2, the value of the function changes from minus 2 to positive 7. That is, if you consider the graph between these two interval, these two values of x is equals to 1 and x is equals to 2, the value of the function at 1 is minus 2, some value here, and the value of the function at x is equals to 2 is some positive value 7, some value here, so that if you consider the curve from this point to this point, you'll note that it must cross the x-axis in this interval. So that this guarantees that the function or the equation that we were solving, that is the equation x cubed plus 2x minus 5, has at least one root in the open interval 1, 2. Has at least one root in the open interval 1, 2. We can then approximate this root by the midpoint of the interval. That is, we can take x naught to be the midpoint, 1 plus 2 divided by 2, which is 1.5. That is probably how we can make our first approximation. With this value in mind, we can now obtain a better approximation using the Newton-Raphson method. We have already derived the formula. That is xn plus 1 is equals to 3xn. Sorry, this is 2xn cubed plus 5 divided by 3xn squared plus 2. This is the formula for solving this particular equation. So we start by setting n is 0. So when n is equals to 0, we get x1 is equals to 2x naught cubed plus 3 divided by 3x naught squared plus 2. This is 5, not 3. The value here is 5, not 3. We can substitute the value of x naught as 1.5, and this will give us 2 times 1.5 cubed plus 5 divided by 3 times 1.5 squared plus 2. And if you work out this value and express the result correct to 4 decimal places, we get 1.3429. That is correct to 4 decimal places. If we set n is equals to 1, then we get x2 is equals to 2x1 cubed plus 5 divided by 3x1 squared plus 2. And we substitute the value of x1 that we have obtained in the previous iteration. That is 1.3429. So we get 2 times 1.3429 cubed plus 5. And the denominator is 3 times 1.3429 squared plus 2. Working out this value, we get 1.3284, correct to 4 decimal places. Increasing the value of n to 2, that is for n is 2, we get x3 is equals to 2x2 cubed plus 5 divided by 3x2 squared plus 2. And substituting the value of x2 that we have just obtained, the value of x2 that we have obtained here, 1.3284, we get 2 times 1.3284 raised to the power of 3 plus 5 divided by 3 times 1.3284 raised to the power of 2 plus 2. And working out this value, we get 1.3283, approximately correct to 4 decimal places. And for n is equals to 3, then we get x4, which will be 2 times x3 cubed plus 5 divided by 3 times x2 squared plus 2. Then we substitute the value. This is x3, not x2. We substitute the value of x3 that we have obtained here, 1.3283, and we get 2 times 1.3283 raised to the power of 3 plus 5 divided by 3 times 1.3283 squared plus 2, and the result is 1.3283 when we work out that correct to 4 decimal places. Now we can continue like this, but it is important to note that the value, the approximation x3 and x4 are exactly the same, 1.3283, when expressed correct to 4 decimal places. And this suggests that when getting the root correct to 4 decimal places, this is the best approximation that we can make. This is the best approximation that we can make for the root of this equation. So that we terminate the process at x4 and conclude that the root of the equation correct to 4 decimal places is x is equals to 1.3283. So this is the Newton-Raphson method for solving the equation f of x is equals to 0. You can see the process is easy. We just start with a function f of x, differentiate that function, then substitute into the formula for solving the equation, the Newton-Raphson method. We can simplify that method first, then take the first approximation and apply the method. So thank you for watching.